So hello everybody. Let's talk about transform margins, structural architecture, their depositional systems and their thermal regimes. Before we start talking about transform, we swing by to look at several things with the strike slip faults. We would represent them as they nucleate and get generated in a homogeneous medium by ellipsoid. That ellipsoid would have a length, it would have a width, aperture. And as this ellipsoid would eventually grow, internal shears and elements of its structural architecture would become more and more mature in central portion. They would remain zero displacement at the edges. And most mature portion would eventually see radial shears feeling each other, eventually getting connected by P shears, connected by pull aparts, and eventually there would be a through-going zone of principal displacement developed. But there's homogeneous medium, but imagine that the system would be layered. And it may so happen that there would be this layer and layer which I'm not showing, and they would be decoupled. And this decoupling could prevent propagation of this fault from upper layer into the lower layer. There could be a detachment fault generated. Lower layer could develop it somewhere else, and they could be connected via detachment. If strike slip faults have large enough displacements, they would need displacement dissipation structures at their ends. And we will be talking about one of these types, about the horsetail structure. We see it here. This is a mesoscale example from Bristol Channel. This is a seismoactive lavic lake fault from California. Basically, what we see is that the strike slip dominated system would change into oblique slips and eventually to normal faults, dissipating structure at the end of fault. Now we can swing to transforms, and we will start going through the literature on continental transforms because there is a lot to learn. Transforms, they usually start as relatively broad zones of different types of faults. At some point, they would undergo strain localization, and during the same time, one of their faults would become dominant. And as we can see from several relatively known transforms, it would capture more than 50% of total plate displacement. But there are other things to learn. For example, case studies and numerical models document that in order to experience development of a continental transform, there should be initiating lithospheric perturbation that helps with nucleation. Every single more known one has a data for that. And they are known to propagate, mostly in a map view, so they become longer, or some of them have a preferred direction of propagation. Our own research from a Coromandel transform margin in East India shows us that they actually also undergo downward propagation. So now we are finally looking at the deformational record of such a transform. Actually part of it, because its Australian part is gone. So we are looking at Coromandel transform recorded by transform margin in East India. What we see is entire system of faults. When you look at the scale, even that the remainder of one's wider transform is relatively wide. We are looking at something varying between 60 to 80 kilometers. It would have its northern horsetail structure. We would call it associated, and I will let you know why. Then there would be a fault pattern characterizing transform sensu stricto, and then there would be a joining horsetail structure. The reason for different names is that apart from you obviously see that they look different, it's the propagation of rift zone and its change into subsequent oceanic segment. So the propagation of these normal faults was towards the west. At some point, they swung, changed their geometry, became oblique slips and eventually strike slips. And they were propagating down towards south and established a horsetail structure, joining it with the eventually failed portion of Kaviri rift zone. But then after continental transform development stage, there was an oceanic continental one that took place after the breakup. After the breakup, there was a spreading center initiated here, and it needed to laterally clear its contact with the future transform margin. In order to do so, it needed accommodation from these strike slip faults. While they were actively accommodating, they kept propagating and eventually cut through its own earlier horsetail structure. So therefore, it's such a non-elegant architecture in comparison with this beautifully developed one. So this one is associated, this one is joining, because the system was joining another segment. Or we can jump to Guyana, offshore Guyana, Suriname. We can look at associated horsetail structure of Guyana transform. And we can see a dissemblance produced from a 3D volume of reflection seismics that we can recognize 6 different strike slip faults. And they are actually frozen in time at different maturity stages. This one is relatively embryonic. It never really evolved further past an echelon riedel shears, while these ones were fully connected. So now let's talk about how continental transform development stage changes into oceanic continental and how that eventually changes to transform margin development. So for that, we can draw a simple map, put 2 transforms, continental ones, and they are linking 3 pull-apart terrains or 3 rift zones. And eventually breakup would take place. This would be trajectory, and there would be spreading centers initiated in those more extensional domains. This one would leave, and this one would laterally migrate along future transform margin. And it would take it a while until it loses contact with future transform margin. And while the spreading center does so, it provides quite some heat for the margin. And while it does so, it also keeps generating newer and newer increment zones of a new oceanic crust. So therefore, the system becomes wider as it migrates. So what this stage basically does is that it migrates in time and space. So this would be segment undergoing development stage, oceanic continental. This one is already transform development stage. Continent-continent contact could be still called as a continental transform. So this transitional oceanic continental one would be somewhere else in younger time. It would be wider. And eventually everything would change into development of 2 conjugate transform margins. So the problem with these transitional stages, the 2 different deformational environments are forced to cooperate. Continental side, where the plate is already there, it's being deformed. So pre-existing plate, lithospheric plate, is deformed by whatever deformation record. Oceanic side would have a deformation taking place coevally with the development of new plate. So while strike slips, for example, here would be at a relatively low angle to sigma 1, sigma 3, over here, if we are looking at intermediately fast spreading systems, strike slip faults would have a tendency to be parallel to sigma 3. So that would mean that these things are stuck with each other and they will do all kinds of pranks to each other, constraining each other. So for example, traveling by spreading center would, like in this example in West Australia, would try to propagate through the transform. And you can see those 2 rift propagation attempts recorded by Sonne and Sonia Regis that eventually failed. But I'm not showing it on this map. Strike slip faults here, while they're active, accommodating lateral passage of spreading centers, they would keep propagating their horsetail structures to dissipate the displacement. And eventually they could run out of continental plate and run into oceanic plate. You can see such a bizarre things, for example, in offshore Guyana. Or if there wasn't continental and oceanic side, but everything was just oceanic, we would have two spreading centers. They would develop overstep region. And eventually they would develop prototransforms. They would rotate. And eventually there would be a sigma-3 parallel transform linking two spreading centers developed. So this would be disorganized spreading. Okay, this would be organized one. We can see that also in nature. This is Iceland. Or one could see oceanic crust feeling cooling effects of a continental crust. So therefore it would have a thinned zone of its thickness. Or we would see bizarre distributions of a thickness of continental crust. This would be a pull-apart terrain between St. Paul and Romanche. And eventually it would separate this spur of relatively thick crust from thick crust of mother continent. So this would be a candidate for marginal ridge. And if it's eventually released by strike-slip faulting, it would be a microcontinent. So this all develops very complex scenario of crustal thickness distribution, and it in turn would control depositional systems. Here we are looking at top to basement map showing banana-shaped ridges and valleys of associated horsetail structure, high plateau and deep basin characterizing transform margin sensu stricto, and isometric highs, isometric lows characterizing joining structure. So they would have very different patterns. This would be high plateau representation of a transform. This would be interior pull apart, inserting a local complexity to depositional systems. Or this would be different parts of a horsetail structure, making a relatively straightforward shot of sediment from shelf to basin more and more complicated, with a lot of processing and storage of sediment. And to wrap up, I have probably two slides on thermal regimes. So this would be the model. Continental transform, two rift zones. They would eventually undergo breakup and spreading center would laterally migrate. And this would be the thermal effect. Breakup would be recorded by two very important thermal transients outlining rift zones making it. But there would be a second transient that would record lateral passage of migrating spreading center that would eventually get out. Thanks a lot for your attention.
Thank you, Michal. Do we have any questions from the audience? And you can feel free to type them in the chat as well. Genreto says, Genreto has a question. If go ahead, Genreto.
Hi, actually, I have a question about the magmatic systems. You didn't talk about them. Are these systems attracting magma, or are they channelizing the magma, or what are the observations?
I guess we both remember the conference we had a year ago, and we were talking about magmatic systems, and we learned that I don't think at the moment we have completely conclusive evidences for one or the other. Kind of a logic would let us think that since there are vertical or relatively steep connection between potential chambers and surface, that there should be preferentially used. And with this question in mind, I was, for example, quizzing people from Australian Geological Survey that work a lot along their West Australian magmatic margins. And I was literally quizzing them whether they could tell that there was more magma along some of these transforms like Zenith Wallaby Perth or Cape Branch would, in comparison to rifted margin neighbors, or whether they would see more magmatism recorded by junctions of these different types of segments. And they couldn't really give me a clean-cut answer, unfortunately. So I think that we have a little bit of research ahead of us on this subject.
Thanks.
Are there any other questions? I mean, I've been really fascinated. I mean, I'm looking at rifted margins off Newfoundland, and the interplay with those and the offshore transforms. It's fascinating to me, and how much those transforms really are a reflection of the inheritance from Rodinian breakup. Even is really fascinating in terms of how it controls the offshore continental margins and therefore the sedimentation that goes in there. In terms of the examples here, how much of inheritance, pre-rift inheritance on these transforms are you able to discern?
With regards to East India, let me just open this one. So this was a Proterozoic orogenic belt. And there was a head-on contractional segment, and they were linked by some kind of a ramp. I'm not trying to tell that a transform is perfectly parallel to that, but it's there. It's relatively close, so it must have felt that.
It's tempting.
And it's tempting. I always remind my students a story of Bruce Rosendahl working 8 years in Africa in search for ideal normofold developed without any effect of pre-existing weakness. And he found one after 8 years. So now imagine that strike slips are even more prone to feel pre-existing weaknesses. So having one totally unaffected would be difficult. And when you look at old rock mechanics experiments like a Donut from 60s, several others, it doesn't mean that it's the weakness itself which directly gets reactivated. No, if it's at high angle to sigma 1, it would pull typical Andersonian location of dominant strike slip a little bit to a higher angle from sigma 1. If it's too close to sigma 1, it would push it towards being closer to sigma 1. But so it makes it very difficult when you work with geophysical data to really blame it on weakness. But physically, it makes sense.